Now we will talk about standard deviation of the sample means. So how wide is this distribution? If we will have a bigger sample size, this distribution will get more narrower. And if we have a smaller sample size, this distribution will get wider. And we all have an intuition of why is that happening. Because the more items in a sample we have, the better we reflect the population. So the sample mean should be closer to a population mean. And we will talk about the formula of how we can calculate normal distribution with a big certainty. So the standard deviation of the sample mean is the standard deviation of a population divided by square root of n, and n is a sample size. Okay, and we will have a formal derivation, formal proof for that. And then I will show you some graphic interpretation to give you just an additional look at it. So we will use a variance because it's just simply easier to calculate it on the variance, and you have to remember that the variance is standard deviation squared. So if we have a variance, we have a standard deviation, and if you have a standard deviation, we have a variance. So the variance of a sample mean. Here we just write the sample mean in a formula that 1n multiplied by sum of all of the items. And here we have 1 divided by n squared in front of variance. And how is that happening? So here we have a multiplication. So if we have that value, it would be multiplied by 1 divided by n. So it would be shrink n times. And let's draw some simple distribution. It doesn't have to be normal, but in this case it is. And we will see what is happening when we shrink it 10 times. Maybe we will write a mean and the standard deviation. And we usually use standard deviation on the graph because we can just show it. This is a standard deviation, okay? And the variance is less easy to show on the graph. So what would happen if you would shrink it 10 times? We can see that all values get smaller 10 times, so the mean gets smaller 10 times, and the standard deviation is getting 10 times smaller. So the variance would be 100 times smaller. Okay? Cool. So now we go from here to here, and this is not so easy, this is not so obvious, so I'd like to spend a little time explaining this. So the variance of the sum of the things is equal to the variance of those things separately. One condition has to be met. There is no correlation or covariance between those picks. Okay? So x1, if you pick something for xy, for example, a kid in this distribution of heights, it doesn't reflect whatsoever on your second choice and the third. They are completely unrelated. And if you want to learn more about correlation and covariance, I made a video about it. I'll put a link in the description and maybe a link in the top corner if I figure out how to do it. So if we will prove this, so if the sum, if it will work for two things, it should also work for multiple things because you could simply group it in the brackets. Okay? So V stands for variance. Variance of those things is equal to expected value of a squared of a value minus the expected value of a sum. Okay, what do I mean? We can look at it as a standard deviation. Standard deviation has this formula, but standard deviation can also have this formula. And this is a standard deviation squared. Okay? This formula. The expected value, the sum of expected value is sum of expected value of the first thing plus the expected value of the second thing. Imagine this, if you have an average height of a woman 160 centimeters and the average value of the heels, how tall would be a woman in heels? Well, 160 plus 10. So we can use that later on. Okay? So we use it here. We will split it into xy minus ey. Then we will group it in a different way. And for now, it doesn't make sense why we do it, but later on it will. So when we do this, we can group it into a and b. Okay? This should be plus. A and b. And you know the formula for a plus b squared is a squared plus b squared plus 2ab. And this squared is equal to standard deviation. Okay? We can see it here. This squared equal to a standard deviation. And we just showed that we can, if we have a sum, expected value of sum of things, we can, it's expected value of one thing plus the other. With a sum, we can split it. So this is exactly what we do here. So this thing here is a standard deviation squared, or a variance. This is a variance of x. Here we have a variance of y, and here we have two covariances of x and y. And if you don't know what this covariance is, watch the video and the link in the description below. But simply, there is no connection between dimensions. If you choose this, it doesn't reflect on choosing this. Okay, so in that way, if this is 0, we have a variance of sum of things equal to variances of those things summed up separately. Okay, so this right here is true. And if this is true, and we have xy, x2, and so on from the same distribution, because we take items to a sample from the same distribution, so xy and x2 and x3 and so on, they are all the same. So we have just n variance of x, or n sigma squared, because variance is a sigma, and this is why we get this here. And here we have sigma squared divided by n, and the variance is a square sigma, so we have to take a root of it, and we have a sigma divided by square root of n. And this formula works surprisingly well. Here we have sample's standard deviation, the actual value from that graph, and here we have sample standard deviation according to the formula. You can see those values are very similar. Here is the proportion of them. It's around 1, so that means that this formula works really well. And I gave you formal proof of that formula, the derivation, but if you want to see a graphical interpretation of why it works, I made the second part of that video that I invite you to watch.